Hey, I'm Charlie Thompson, and welcome to the Lab 7 Atmospheric Stability How-To video. In this video, I'm going to go over how to do 3 practice problems. I've made a link to a handout, so all you need to do is click on the link, and it'll open up the practice problems for you so you can follow along as you're going through the video. So, the first example, we're going to take a parcel of air and we're going to lift it up. The activities we're going to do, the skills you need, we're going to find the dew point temperature, the lifting condensation level, the final specific humidity, because as it cools, you're going to lose water, and which is another way of saying the grams per kilogram of water vapor that condensed. Everything that condenses becomes a cloud, so that's what's going on. So we're going to take a parcel from the Pacific Ocean up to the summit of Mount Waialeale on the island of Kauai at 5,100 feet. Assume that the temperature on the ground is 81.0 degrees Fahrenheit and the parcel has 90% relative humidity. So what's the first thing we're going to figure out? Well, what's the parcel's specific humidity? So the formula for specific humidity, if you're given the temperature and the relative humidity, is max specific humidity at that temperature times relative humidity equals specific. So we look it up on the chart. With the temperature is 81 degrees, it's in between 82 and 80, so we use the cooler one of 22.8 grams. 22.8 times 0.95 is 21.66, and that rounds to 21.7 grams per kilogram. So now we know the initial specific humidity of the parcel. And if we know that, we can find the dew point, or rather, the dew point temperature of the parcel. So if we know that it's got 21.7 grams, we look it up on the chart. It's in between 22.8, 21.4, so we're going to use 78.8 as the temperature, the dew point temperature of the parcel. Once we know the dew point temperature, we can find the lifting condensation level. So the formula for that is starting temperature minus the dew point temperature. That tells you how many degrees you have to cool. And 5.5 is the dry rate. That's the rate the parcel is going to cool until it cools to dew point temperature. So we find out how many degrees it has to cool, divide that by 5.5, and the answer is going to be thousands of feet of lifting to the lifting condensation level. So we plug those numbers in. The starting temperature was 81. The dew point temperature is 78.8. That works out to 2.2 degrees. Divided by 5.5 works out to 0.4. Because the units for this are thousands of feet, that's 0.4 thousand feet, which is 400 feet. So now we know the lifting condensation level. We know at what point above which we will start cooling at the moist rate. So above 400 feet, as the parcel keeps rising, now it's going to cool at the moist rate. And the temperature at the lifting condensation level, we know the dew point temperature, and it's going to get colder by the amount of lifting times 3.3 degrees of cooling. So as the parcel rises, it's going to cool 3.3 degrees per thousand feet. So plugging in the numbers that we've got, we're going to be lifting at 4.7 thousands of feet because we're going from 400 feet to 5,100, which is 4,700 feet, which works out to 4.7 thousand feet. 4.7 times 3.3 gives us 15.51 degrees of cooling. We're going to round that to 15.5. So our dew point temperature, 78.8, minus the amount of cooling, 15.5, gives us 63.3 degrees Fahrenheit up at the top of Mount Waialeale. So now we know the temperature at 5,100 feet. If you know the temperature of a parcel that's already cooled to dew point, we know the specific humidity. We just look it up on the maximum specific humidity chart. The temperature is 63.3, which is in between 62 and 64. So we're going to pick the cooler, and we're going to say the specific humidity is 12.2 grams per kilogram. And now we're going to find out how many grams of water vapor condensed as the parcel rose from sea level to 5,100 feet. Well, to find how many grams of water vapor condensed, you need to find the specific humidity at the beginning and subtract from that the final specific humidity. So we started with 21.7. The final specific humidity is 12.2, so the parcel lost 9.5 grams of water vapor per kilogram of air as it rose from sea level to 5,100 feet. Well, that wasn't too bad. Let's do another one. We're going to take a parcel and we're going to lift it up. We're going to find the relative humidity for that air parcel, the dew point temperature, the lifting condensation level, the final specific humidity, how much water vapor condensed out of that parcel of air. We're also going to find the temperature of the atmosphere, and we're going to find if the parcel is stable or not. So now we're going to add finding the temperature of the atmosphere by cooling the atmosphere at the environmental lapse rate. And then we're going to compare the temperature of the parcel to the temperature of the atmosphere to see if the parcel is stable or unstable. So let's get started. Given an air parcel, 95 degrees with a specific humidity of 14.7 grams per kilogram and an environmental lapse rate of 6.5 degrees per 1,000 feet of lifting. So the temperature of the parcel, temperature of the atmosphere, they're going to be the same temperature on the ground. That's just redundant information, but I didn't want to have anybody wonder, well, he gave us the temperature of the parcel. What's the temperature of the ground? Well, if it's on the ground, the parcel and the ground, they have the same temperature, 95 degrees. So let's find the relative humidity of the parcel. The formula for relative humidity is specific humidity divided by the maximum specific humidity times 100, expressed as a percent rounded to a whole number. So let's plug in the numbers. So we know that the specific humidity is 14.7. That was given. We know the temperature is 95 degrees. Looking at the chart, 95, the maximum specific humidity is 36.4. So specific divided by max specific works out to 0.403. Multiply that by 100, round it to one digit, and we get 40% relative humidity. So now let's find the dew point temperature of the parcel. So from the chart, we know it's got a specific humidity of 14.7 grams, and the dew point temperature for 14.7 grams of water vapor is 68 degrees. And now let's find the lifting condensation level. The formula for that is temperature minus dew point temperature divided by 5.5 gives us how many 1,000 feet you got to lift it to the lifting condensation level. So plugging in those numbers, temperature is 95, the dew point temperature is 68. 95 minus 68 gives us 27 degrees of cooling. That's how much it has to cool from its current temperature to the dew point temperature, 27 degrees divided by 5.5. Remember, that's the dry rate. Gets us 4.909, which means 4.909 thousand feet, which works out to 4,900 feet. Remember, LCL, you round to 100 feet. Now we know the LCL, we know the altitude, we know the dew point temperature, 68 degrees at 4,900 feet. We're going to lift it up to 14,500 feet, though. That's pretty high. And we're going to cool it at the moist rate. So let's figure out what the temperature of the parcel is after we lift it above the LCL. So the formula for that is we're starting with the dew point temperature, and it's going to get cooler because we're going up. How much lifting times 3.3 degrees of cooling for every 1,000 feet. So plugging those numbers in, we are going from 4.9 thousand up to 14.5 thousand. So that's 9.6 thousand feet of lifting, 9,600 feet of lifting. And it's going to cool 3.3 degrees. So that works out to 31.68. We're going to round that to 31.7 degrees. So our starting dew point temperature was 68 degrees. It cooled by 31.7. So the new temperature of the parcel is going to be 36.3 degrees. Now we know the temperature, we can find the new specific humidity because the whole time that parcel was cooling, it was losing water to condensation. That's why it's cooling at the lower rate of 3.3 degrees. So once again, we know the temperature, 36.3. 36.3 is in between 35 and 37. So the new specific humidity is going to be 4.4 grams per kilogram of water vapor. So we started off with 14.7. We ended up with 4.4. How much water vapor condensed as the parcel rose and cooled. So starting specific humidity minus ending gives us the starting was 14.7, the ending was 4.4, so that parcel lost 10.3 grams of water vapor per kilogram of air. So I think we're done with the parcel for now. Next thing, I want to know the temperature of the parcel. And the parcel, remember, cools at the environmental lapse rate. That will always be given to you. In this case, the ELR is 6.5 degrees per 1,000 feet. Plugging those numbers in. The formula for that is starting temperature minus the 1,000 feet of lifting times the rate of cooling. In this case, our starting temperature was 95 degrees. We're going up 14.5 thousand feet, and we're cooling at 6.5 degrees per 1,000 feet. That's the ELR. It's given to you. 6.5 times 14.5 is 94.25, which rounds up to 94.3. 95 minus 94.3 gives us a temperature for the atmosphere of 0.7 degrees Fahrenheit. So remember, the atmosphere cools at the ELR changes and will always be given. And now we can answer the question, is the parcel going to keep rising, or is it done rising? Is it stable, in which case it's not going to rise, or is it unstable? So the parcel is unstable. The temperature of the parcel is 36 degrees. The temperature of the atmosphere is 0.7. So that parcel would keep rising because it's warmer. The temperature of the parcel is warmer than the temperature of the atmosphere. Again, not too bad. Okay, that went pretty well. Let's take a look at example number 3. In example number 3, we're going to take a parcel. We're going to lift it. So we'll get condensation. Water's going to condense. We're going to lose water, so the specific humidity is going to go down. And then we're going to drop it down so it'll warm up, and the relative humidity should go down. So in this example, we're going to find the dew point temperature, the lifting condensation level, the final specific humidity at the summit, how much water vapor condensed on the way up, the temperature of the atmosphere at the summit, and then is the parcel stable at the summit. After we're done with the parcel at the summit, it's going to drop down and we will calculate a new ending temperature, the specific humidity is going to stay the same, and we'll calculate a new relative humidity because the temperature will be higher. So the maximum specific humidity will be higher, but the specific humidity will be the same. So let's jump in. So in this exercise, we're going to take a parcel of air up to the summit of Mount Rainier in Washington State at 14,400 feet, and then we're going to drop it down into Yakima, Washington to an elevation of 1,000 feet. You are given an air parcel at sea level at 59 degrees with 40% relative humidity and an environmental lapse rate of 3.8 Fahrenheit degrees per 1,000 feet. So let's take a look at the following questions. So the specific humidity is the first question. What's the specific humidity? So we're going to open up the Lab 6 handout. We're going to find the specific humidity. So go to the specific humidity section. And we are given a temperature and a relative humidity. So we know if the relative humidity is 40%, then this parcel of air, given a relative humidity of 40% at 59 degrees, we know it has 40% of what the maximum is at 59 degrees. So we need to find the maximum specific humidity. And again, hopefully you still have the Lab 6 handout handy. And we're going to look up 59 degrees. The maximum is 10.6. 10.6 times 0.4, that'll get us 40% of 10.6 grams. That's 4.24 grams, which is going to round to 4.2 grams. So now we know the specific humidity, and the next thing we're going to do is find the dew point temperature. So we know what the temperature is, or rather we know what the specific humidity is, 4.2. So that's in between these two. So we're going to take the cooler temperature, since we won't get condensation at 35.6 degrees, but we should at 33.8. So the dew point temperature of a parcel with 4.2 grams of water vapor, the dew point temperature is going to be 33.8. So now we know the dew point temperature, we know the starting temperature, we know the dew point, so now we can find the lifting condensation level. So the formula is temperature, 59, minus dew point temperature, 33.8. That'll tell us how many degrees it has to cool until it cools to dew point. Now we're going to divide that by 5.5. 5.5 is how many degrees the parcel is going to cool as it rises and cools at the dry adiabatic rate. So 59 minus 33.8 works out to 25.2. 25.2 divided by 5.5 gives us 4.581. But remember that 4.581, the units for that are thousands. So that's going to actually represent 4,581 feet. Remember, we're rounding to the nearest 100 feet. So we look at the 5, and the number to the right is an 8. 8, the rules of rounding, if this was 5 or higher, we're going to round up this number. So we do. And the lifting condensation level is going to be 4,600 feet. So now we know the lifting condensation level. We know the temperature of the parcel at the lifting condensation level. Now all we have to do is lift it up to 14,400 feet and see how much it cools. So we're going to take the dew point temperature and we're going to subtract from that the lifting in thousands of feet, and we're going to multiply that by the moist rate. So we already know the temperature at the LCL. We're going to go up to 14,400 feet and cool it by 3.3 degrees for every 1,000 feet. So from 14,400 to 14,400 feet to 4,600 feet, that's 9.8 thousand feet times 3.3 is 32.32. So our dew point temperature of 33.8 minus 32.3 gets us a temperature of the parcel at the summit of 1.5 degrees. If we know the temperature of the parcel, then we know the specific humidity. Since the parcel hit 100% relative humidity and continued to cool as it rose, it's going to still be at 100% relative humidity. So the specific humidity of the parcel at 14,400 feet is going to be the same as the maximum specific humidity of the parcel because the parcel's at 100% relative humidity. So we look it up from the maximum specific humidity chart. And because we've got the temperature is 1.5, so we'll use 1.4, and the maximum specific humidity is going to be 1.1 grams. Now we need to calculate the temperature of the atmosphere at 14,400 feet. We know the temperature of the atmosphere at sea level, that's 59 degrees, and we know the environmental lapse rate, 3.8 degrees. Okay, so now we're going to find the temperature of the atmosphere. And to find the temperature of the atmosphere, we're going to use one of the lapse rates. We're going to use the environmental lapse rate. So we know the temperature of the parcel at sea level is 59 degrees. So we're going from sea level up to 14,400 feet. And it's going to cool 3.8 degrees for every 1,000 feet. So 3.8 times 14.4 works out to 54.72, which is going to round to 54.7. So that's how much cooler the parcel is going to be. So we're going to take the starting temperature and subtract how much cooler it is. The starting temperature of 59, starting temperature of 59 minus 54.7 equals 4.3 degrees. So the temperature of the atmosphere at 14,400 feet is 4.3 degrees. So we know that the temperature of the parcel is 1.5 degrees, the atmosphere is 4.3, so the parcel is stable because the parcel is colder than the atmosphere. All right, parcel stable. So now the parcel of air is going to sink from 14,400 feet down to 1,000 feet. As it does so, it's going to heat at the dry adiabatic rate. So to calculate the parcel's temperature, we're going to take the starting temperature at the summit, 1.5 degrees, and add to that how much warmer it's going to get. Sinking in thousands of feet, times the dry adiabatic rate of 5.5. So it's sinking 13.4 thousand feet. Remember, the summit is at 14.4. We're dropping down to 1,000, so that's 13,400 feet times 5.5. That works out to 73.7, plus the starting temperature, or rather the temperature of the parcel at the summit was 1.5. So 1.5 plus the degrees of warming gets us to 75.2 degrees. And remember the next thing, the parcel's specific humidity is the same. The parcel's going to warm, but it's not going to gain any moisture. So the parcel's specific humidity is still 1.1 grams. The only thing that's changed to the parcel since it left the summit and it sank is it heated up. So now that it's heated up, we need to find a new relative humidity because we have a new maximum specific humidity. And to find that, we just look it up on the chart. And we're going to calculate relative humidity equals specific divided by max specific times 100. The specific we know is 1.1. We need to find the new max specific. So with a temperature of 75.2, the maximum specific humidity is 18.9. So we're going to take the specific humidity of the parcel, 1.1, divided by the max, 18.9. That gets us 0.58. We're going to multiply that by 100 to make it into a percent. That gets us 5.8. And then when we round that to a whole number, that gets a relative humidity of 6%. That's all I've got for Lab 7. I hope it's making sense. I hope it makes more sense. If it's not, please, please, please give me a call. I've had a bunch of phone calls this week with students. And they were all helped. Nobody cried. Everybody was happy. It was a good scene. So if you have any questions, please, please, please let me know. I promise you 5 minutes on the phone can clear up confusion and you can get on with your life.